hi everybody, good afternoon. So first of all, let me thanks to the organizers for set up this very nice conference and for select this very nice place to have this reunion. So yep, that said, I'm going to talk about Lorentz invariance violation, and this is a work that I have been performing with Rodrigo Guedes-Lang, which is a PhD student, Professor Peter Sousa, which is here also in the audience, and myself, I'm a postdoc, all of us working in Instituto de Física of São Carlos. So, yeah, that said, this is how I'm going to spend your next 20-25 minutes. We're going to go from some LIV models to some experimental constraint, moving through some phenomenology in the middle. So that said, let's start with Lorentz invariance violation. So why Lorentz invariance violation and which Lorentz invariance violation we are going to use? So why allow me to stress first that, as you know, there are 4 fundamental forces on nature. 3 of them are very nicely described by the standard model, while gravity, on the other hand, is described by general relativity. Allow me to stress that these 2 models are the best theories that describes the 4 fundamental forces. There are not conflicts of prediction from either of them. However, while the standard model, as you know, is a quantum theory, general relativity is a geometrical theory, and they are fundamentally different. So this huge, however, has motivated different theoreticians, different models, to look somehow some quantum theory gravity, like string theory or loop quantum gravity. Among these new models, so new physics will arise, new features, and among these new features, you can find, for instance, higher dimensions, new brain-world scenarios, non-competitive geometries, and among the options, there is the possibility that there is some Lorentz invariance violation. So, by finding some signatures of Lorentz invariance violations, we could climb some clues on what is the solution, or if there is a solution in there. So which Lorentz violation we are going to use for this analysis? Well, as you know, from there has been shown from different theoretical models that you can introduce Lorentz invariant violation by changing the Lorentz invariant dispersion relation, which is wrote here, square minus p square equals to m square, basically, for each particle. So you can introduce LIV by adding this new term, which this epsilon is going to be a general function of the energy or the momentum, and this A can take the form of the energy or the momentum. If you follow the Coleman and Glasgow approach, you can expand this term as a series, as is worded here, and you can then study each term per time as a leading order. So you can rewrite this dispersion relation that is worded here, is square minus p square, plus minus this delta that is going to contain all the LIV information, plus A at leading order n, plus 2 with A can be E or P. This delta is going to change depending on the model that you are assuming that is behind this correction. For instance, if you are assuming that there is some effective field theory, this epsilon is going to become the coupling of the theory, and M can take the form, there will be an energy scale that protects the features at lower energies. M can take the form of the quantum gravity scale or the Planck energy scale. So without loss of generality, we can rewrite this term just by calling that there is some Lorentz invariant violation energy scale. So that said, in the follow, we are going to focus in the leading order n equals 1 and n equals 2. And well, now that we have a model, it's time to couple with a target in some astrophysical scenarios. And for that, we have selected gamma rays. And gamma rays, as we know, can interact with the background and produce a pair, as is worded here, a pair electron-positron. And if you do the kinematics by inserting this new dispersion relation, you can parameterize the threshold of the process, as this expression is worded here, where x is going to be the energy of the gamma ray over the Lorentz invariant threshold. This lambda here in this polynomial expression is going to contain all the LIV information. If you do the math, which is quite straightforward, you can find the threshold, the minimum energy that the background photon needs to produce a pair. To look at which type of phenomenology you can expect, we can plot this function as is wrote here, and we are going to find 3 different scenarios. When this lambda, this is the LIV parameter, is 0, you're going to recover the LI scenario, and every time it crosses 0, you're going to find a solution, so that means there is a threshold. So here, there is a threshold for power production in the LI scenario. If you shift the lambda for negative values, you are going to shift the threshold to lower energies, and you can see how the different scenario is from the LI. However, if you assume that if lambda is positive, you are going to shift the threshold to higher energies, and besides that, there is that could be a second threshold in the equation. That means that there will be a suppression of the power production in this region. So this phenomena can be called the subluminimal case and the superluminal case, and for this work, we have chosen only to work in the lambda negative scenarios. So now let's go further in this answer to work with astroparticle physics. And as you know, gamma rays can be emitted from some sources. They're going to propagate and interact with the background until they reach the Earth. So here in this plot, I have the energy of the gamma ray against the energy of the soft photon, the background photon. And every configuration that that falls here is not going to produce a pair. However, if you move above this red line, which is the Lorentz invariant threshold, you will be able to produce a pair. This is what we call the pair production area. When you introduce LIV, this region is going to be changed, as is marked here in different colors for different LIV values. So for instance, for 10 to minus 20, in this scenario leading order equals 0, this is the region that allows pair production. If you change the LIV, you're going to extend the pair production region until you reach the LI scenario. So what else can be said of this plot? Well, depending on which type of gamma rays you're trying to analyze. For instance, if you're targeting TeV photons, 10 to the 12 EVs, if you're looking for LIV signatures, you're going to focus in this section, and you maybe want to consider the EBL as your main contribution to the background, because it's the dominant at these energies. So that allows us to target different observatories, which is going to tell us different types of phenomenology to focus. If you're looking for deeper LIV effects, for instance, 10 to the 18 EVs, you can use the CMB background to look for signatures and targeting some phenomenology to, for instance, the Pierre Auger Observatory, which we are going to do in the next slides. So, okay, that said, now that we have some photons, we have a LIV model, we need to compute how these LIV effects propagate from the sources to the Earth, and for that, we are going to compute the optical depth. We know from the standard theory that the optical depth, this tau, can be computed by this expression, which contains three main parts. The first one, that is the distance element, it's here, and for that we're going to assume lambda CDM, the background density photons, which is here, and the pair production cross-section. So in order to introduce LIV, we know that the threshold is going to change, so we are going to input that this information into the computation of the optical depth, and that is going to also affect the cross-section. And now the optical depth is going to depend also in the leading order of the LIV correction and the LIV energy scale. So this is our first result on this talk. This is the optical depth, including LIV. Here I have the energy of the gamma ray and how further we can expect they travel without being absorbed by EVL in megaparsecs. So 10 to the 12 and TeV photon can travel some hundreds of megaparsecs. If you follow this black line, this is the LI scenario and how it changes with the energy. So for instance, you can see here the peak of the CMB, 2.7 kelvins. And in color, there is how it changes when you introduce LIV. So now, for instance, you look here, you can expect for if a source emits a photon that travels further instead of being reduced at this point. So this is results for n equals 1 and n equals 2. And basically what I'm saying is the effect of LIV is going to give you more photons at different energies. So these different energies will depend on the background density that you focus on. For instance, you can take a look at the EVL region, which belongs here. So if you increase the LIV effect, eventually you are going to suppress and change this region. There is also the region that we have considered as the CMB. You can also see the shape of the CMB density here. And finally, but not least, the background density of the radio photons. So That's it. Now that we have some phenomenology to consider gamma rays, we can focus, for instance, in the TeV gamma rays. So that means the EVL window. For that, allow me to define the AVL attenuation, A, which is going to be just E to minus T, minus tau, where tau is the optical depth. And the LIV effect is going to depend on three main things. The energy of the gamma ray, of course, the LIV energy scale, because the pi production threshold, and theta, their distance to the source, because the optical depth, which makes sense. So here in this plot, to illustrate this is what I just told you, there are two scenarios for different redshift, theta 0.03 and theta equals 0.18. You can, if you follow the continuous blue line, you are going to find the LI prediction, where once is zero attenuation, there is no attenuation here, and as you increase the redshift and the energy, you can see how the photons will be attenuated by EVL. So you can see there is an abrupt end in both cases, but changes with the redshift. In addition to that, here I have three LIV scenarios for three different LIV scales, and you can see that there is a prediction of a recovery flux at higher energies, above 10 TeVs for this redshift, and higher for this redshift. So if you can ask if there is already some constraints using this idea, and in fact there is. For instance, you can see this analysis performed by the Markarian 501 with the HES data. So you can see here that the data almost follow the LI prediction, and by that you can constrain all the scenarios, the LIV, that does not fit this data. There is already also some predictions by using CTA. This is some simulations that were presented in the CRC 17. So what we have in the table is that if we can do something better than that in this energetic window, and in fact, we can ask, why use only one source when we already have like hundreds of sources in the TeV catalog? So in order to do that, we need to understand which sources have the potential to show some LIV signatures. As I told you, as I show you from Markarian 501, there are some beams that are not able here, for instance, to distinguish between LI and LIV. Also, you can see here that there is no distinguish between the two scenarios. So we have a proposal to regions, the LI and LIV region, and split it by these vertical lines for the HLIV, where they are different about 10%. By doing that, we're now able to select these sources that have the potential to study or to constrain LIV. We found that for LIV that is compatible with the current limits of LIV. So this is the scenario. This is the 111 sources plotted as a function of redshift and as a function of the maximum energy that they have in their spectra. And we have found 18 spectra from 6 sources that have the potential to show LIV effects, or in the worst case scenario, to constrain LIV. So this is still work in progress. We are highly detailedly analyzing these sources. And so stay tuned. New results and interesting results are coming in this region. So following now to the CMB regions, where for what we have proposed to study the GZK photons. So what are GZK photons? Well, imagine that you have, again, a source that is emitting protons, and those protons are going to interact with the CMB. They are going to produce their resonance, and this resonance is going to produce pions, and these pions are going to decay into gammas. This gamma is a secondary flux expected from ultra-high cosmic rays, and they are so-called GZK photons. So now we're going to compute this flux, including LIV. For that, we know that the GZK photon flux is highly dependent on the model of sources. For that, we have proposed to use a power law as ultra-high spectrum, where this gamma is the spectral index, and we have used 4 different scenarios with different species of cosmic rays, going from those that are pure proton scenarios, for instance, this is C4, and C2 is pure silicon, assuming that we get that cosmic ray is mostly heavier made for heavier composition masses, and C3 and C1 are mixed scenarios. So in addition to that, we also need to select some model of distribution sources in the universe. We have choose 5 different scenarios, going from the most naive that we assume that every source is uniformly distributed in the Cohomolving model, just as a reference. And we have additional other 4 scenarios that are what here you can compare in this plot, which is through time. I'm going to go to the next step. So once we have some source distribution model and also the injection models, we need to propagate everything from the source to the Earth. For that, we have used the Sierra Propa 3 and LCAS software, and for that we need a lot of a combination. We need to combine all the sources and all the distribution sources and a lot of LIV. And for that, we have asked Rodrigo, who is a brilliant and enthusiastic student, to do all the possible combination of these flux. He made the task, and we have found the integral flux of GC that have photons, including LIV, for each source model and for each source evolution model. Here is an example for the R5 scenario. You can see here the integral flux of the GC that have photons. So you can see how it changes for different models. This is assuming already some LIV, and this is the distribution sources. You can see there is not much difference among them for this particular LIV. By using different LIVs, different LIV's coefficients result in a shift up and down of this effect. So now that we have a prediction of the G-stack photon flux including LIV, we can go to the experiment and say if they are compatible, there are some signatures of if we can constrain this or Lorentz invariance violation model. So here is our result for the scenario n equals 1. Here are the R5 distribution source scenario for the 4 different injection models. So some interesting things here to see is that the black line in each square is the LI prediction, and the red line is the most LIV scenarios. So that means that we have maximized the effect of LIV. So any photons above these red lines does not belong to LIV predictions. So this is an interesting result in these plots. So now we can compare with the latest Auger upper limit to the photon flux. So here they are in gray and in these dark arrows. And you can see, for instance, in this scenario that these LIV scenarios, so here you can imagine that you have a lot of lines belongs to different LIV scales, are already discarded in this scenario. But we have a lot of possibilities. And for that, we need to ask again to the experiment which of these models is the right. And experiment had told us that the combination of C3 and R5 already describe very nice the data of ultra high energy cosmic rays. So this scenario is or still have some LIV prediction compatible with the data. However, there are already some that can be discarded. By doing that, and this is almost my last plot, here are some limits that comes from this, by comparing these predictions with the Auger data, C3, R5, and you can see our limits, and you can compare with previous limits where they are studying or try to study the GC-Teka photon flux, including LIV. Notice that they were made in 2008. That's at the beginning of Pierre Auger. And also, you can compare with the limits given or set by some TeV approaches, TeV techniques. So in this sense, these limits are, well, we have recently published this work in the Astrophysical journal at the beginning of the year. And finally, my conclusions, because I think I'm over time. So 3 main conclusions. We have computed the mean free path of the power production considering LIV. We have obtained the GC-Teka photon flux including LIV. And finally, we have set some LIV limits compatible with the most updated data of ultra high energy cosmic rays. So that's it. Thank you very much for your attention.